So now I'd like to introduce our keynote speaker, who's an industry leader with expertise in artificial intelligence that extends to the energy, aviation, and healthcare sectors. Dr. Colin Parris is Senior Vice President and Chief Technology Officer from GE Digital. We are delighted Dr. Parris agreed to join us today to give an industry perspective on, what I'm sure for him has been the digitization of everything over the course of his career, and applying artificial intelligence to the energy sector and beyond. Dr. Parris.
Okay, thank you very much, Dr. Murray. Hopefully you can hear me properly.
I can, certainly.
Excellent, excellent. Good, so let me, I see the charts are up, which is always a good thing. So let me tell you a bit about what I'll be talking about today. The talk is entitled Digital Role in the Future of Energy. But if I listen to what Dr. Murray was saying, as well as Evan, I mean, we're going to be tied quite nicely into our view of what's happening with energy and analytics. But let's talk about the agenda here. So what I'd like to tell you about on the agenda, you'll see there are four things, right? The first, I want to frame the forces that are impacting the market and driving forward right now. To give you a view how GE thinks about it, much of my talk here will be in the context of GE. Because while we're dealing in the energy, we have two prime things in mind, right, in this industry. One is to deliver value for our customers, and the other is actually to do so at a cost that actually makes it profitable for us as well. So we'll talk about those forces and those drivers. The second, because we're talking so much about, the digital nature of things, I'll talk to you about what's been happening overall in different parts of the industry as we talk about the digital phenomena occurring in the consumer sector, and we'll use those because a lot of those deal with the fact that you can get technology now at volume and great insights, and we'll show you how you use those in the industrial sector so that you can deliver value to those. The third thing is I'll talk about something specific to that, which is digital twins themselves. The digital twin itself is the thing, the entity we use, a combination of physics and AI and analytics that allows us to do many of the data analytics things we're going to do. And then finally, what I'll do is give you some examples of how it delivers value, and then talk about one or two technologies that we will be using, advanced technologies to drive this into the future. Okay, so this chart will talk a bit about the forces shaping the energy market here. So as you can see, there's about four forces, right? I'll talk to decarbonization, efficiency, decentralization, and digitization. So in terms of decarbonization, I think, given the audience here, I think everyone here is fully up to speed on most aspects of that. Let me give you the part that we think about. One of the things that is happening as a result of decarbonization is the rise of renewables. We all know that. But what the rise of renewables also does at the same time, it has a profound effect on the actual power generation assets that are right now, in play. We have a number of natural gas assets, a number of coal assets. So when you bring these things to bear, how do you actually tie these things together and get them to work in a way that makes sense? Right now, renewables, the rise of renewables itself, whether it be the wind or whether it be the solar, it's not enough right now to give you the amount of energy you need on the planet. So you're combining those, with the assets that you have that are fossil-based. The other aspect of it is that even when you do that, the renewable assets are intermittent. So whenever the sun is not shining as you expected, or the wind is not blowing as you expected, you have to bring these systems up to bear. When you bring these systems up to bear, quickly, they no longer run at base load, they're cycling, they're going up and down based upon the amount of energy you're getting from renewable sources. That itself causes inefficiencies, which results in, more cost, but also it produces more carbon. So there's a tie-in between the systems you have now and what you're going forward in the future as you look at these decarbonization aspects of things. This is all part of the dynamics. If you think about efficiency, we talk at length about, we're going to electrification, and what we're seeing there is that we have a number, of smart buildings, smart factories come into play. We're bringing some of these capabilities into play. Well, those capabilities are great because in many cases, what you find is they have systems that monitor them, manage them in certain ways, and so you can get a much more better understanding about the characteristics of these things, and these characteristics then allow you to understand that demand better. So we see the rise in terms of the desire for efficiency, but at the same time, there's that desire for efficiency. We are also capturing more data, which can help us going forward. That's a dynamic we want to exploit. Then there's one that deals with decentralization. There is prosumers as well as, again, because of the drive to do electrification, you have many decentralized sources showing up. And those decentralized sources show themselves up in a variety of ways. Some of them could be, solar rooftops that you see in many of the residential areas, but also you have a number of things like electric vehicles that also show up. And the grid has a responsibility to understand what are all these new distributed resources that are coming to bear. What is the needs that they have, the requirements they have? How do I understand them? And how do I orchestrate them in a way that makes sense? Or can I possibly even utilize them in the event that I don't have the ability to actually generate the power that I need, as occurred in California? That's another powerful dynamic you see. And then the dynamic we're all here to talk about is that one of digitization. I'll spend a lot of time talking about that one, but let me give you 2 key points that always resonates with me. The first for me is that, and I've lived through this, in my career in IBM, in my career in GE right now, it's one of the few technologies in which the growth in performance is sort of balanced against the drop in price, both occurring at the same time. Not many technologies can do that. If I look back 10 years ago and I look at what $1 10 years ago would buy me now in terms of processing power, it's 40x. I get 40x improvement over the last 10 years. Same dollar gives me 40x with more processing power. Bandwidth is in the 30s. Storage is in the 20s, high 20s, right? So you have a capability in terms of massive performance, while in fact the cost drops. You can use that game both ways. I can either buy the performance or I can get mid-range performance at a much lower cost. That's powerful as a technology. The other aspect of this technology that makes it so interesting is that everything that supplies data to it, whether it be some of the meters we have, the sensors we have, those things are significantly dropping in cost. If I look at the last 5 years, we have seen a 60% drop in cost in some of the key sensors that we use in our systems. But that, again, it's profound, because now we can put more sensors, we can use sensors in certain ways, and we see that becoming even better in the next 5 years. So that capability becomes very profound for us as things get digitized, and then we have the ability to use that data and compute and store it in a manner in which it gives us insights. So that's the dynamics that you see. Now, while those dynamics are happening, our customers are asking us for things. The first thing they ask for is, let's make sure it's safe. We take that for granted. But then the next thing after that is, how do I actually get more profit? How do I increase my productivity? How do I increase my revenue? At the same time, how do I manage all these new government regulations that are showing up, and deliver what needs to be delivered? Then how do I adapt to my markets? In many cases, customers are saying to us, I want more renewable energy. Tell me how much renewable energy I'm getting delivered to my house or my business. How do I manage to fit that in? How do I talk about the fact that many of these systems I have to gather data are 20, 30, 40 years old, this internal obsolescence? You've got to do all of these at the same time. So imagine managing all the dynamics and at the same time managing all of those customer requirements. So how do we figure that one out? If you could jump to the next slide for me. What we do is we begin to take a page in our industrial world out of the consumer world, right? If you'll see in this slide here, we unabashedly borrow from what we see occurring with some of the key market leaders in the consumer world, because they've found a way to utilize technology, to use that data to gather insights, and the insights allow them to actually make good decisions that are optimal, and those same capabilities, those same insights allow them then to actually go drive work or take an action that also is optimal, all of it running on a digital fabric. What if we could do that in our industrial space? So let me walk you through what that looks like. And so if I think about these market leaders, there are 2 things that come to mind. One is the notion, and you've seen some of the names, right? In terms of the rapid growth. And as a business person, I always think about that. So for instance, you look at Amazon in 2018. 2019, I think they did $278 billion worth of revenue. Not market cap, revenue, right? If you look, and this is a company, Amazon, that's 24, 25 years old. If you look at Google, another great example, what you see there is about $146 billion of revenue. And that's a company that's, again, in its 20s. Now, I've been at IBM. IBM, to get to $100 billion, it took roughly 94 years. In GE, it took 101 years. You have companies that are in the $200 billion mark, and they're 24, 25-year-old companies. That rate of growth was based upon certain key things. And a lot of it, when you look back, is the ability to use that data to actually create a connection, to give them the ability to make good decisions and then act on those decisions. We see the same thing happening with a number of leaders that I have listed there, all using that data to do that. Now, how do they use the data? If you look towards the right, what you see here is the two aspects of it. One is this notion of a business model. How do I create value? Can I use that data to get enough insights? So for instance, in Amazon, they use the data. I am a member of Amazon Prime. They look at what I buy. They look at what I look at in terms of the ads. They look at what I've bought, recently, what is given to me, what I've done historically, and they can create insights on what Colin should want to buy. And that's what they do. They create those insights using the data. Now, based upon that data, they also do things. They also then generate a workflow. If I select something, what you instantly see happen is that workflow is generated where this goes off into one of their warehouses. In many cases, if it's a single item, it quickly goes and it gets dispatched to a Kiva robot. The Kiva robot goes out, it grabs it, it drops it in a box. The box goes down a conveyor line, the box folds in, it's taped automatically by a robot, and that thing comes out. Humans don't touch it. The entire workflow was a digital workflow. Now, in terms of if you buy 2, 3 things, and sometimes it has to be packaged the right way, they've got to add bubble wrap and everything else, yes, the humans may get involved. Or if it's at a different, smaller site, not one of the much larger warehouses, humans get involved. But the idea is a workflow. And that workflow allows them to operate at a certain speed. And that's why last year they had 319 million, buyers, people who buy from them frequently. That idea is a profound idea for us. In fact, we took it and we began understanding this notion of a digital operating model. So traditionally, you have a bunch of human processes with digital support. What you have now is a digital process, and you insert the human whenever you need. Before, you had human insights using data. Now you have digital insights. Then you add occasionally, maybe a human expertise because it's something new that you've seen. And before, you had a limited scale. Now it's an unlimited scale. So if you take that idea, what can you do with it? So if you jump to the next page, I'll tell you a bit about what we've done with it. We've taken the same idea for the last 5, 6 years we've been working on this. And we have created this thing that we call the digital industrial transformation using something called a digital twin. So we take all of the knowledge we have about the design, manufacturing, the operations, and the inspection part of it. And what we do then is we add to that the data that we're gathering, the data that happens operationally, whenever the asset is performing, the data that happens when we do inspection, the data that comes out of the sensors that we have in the monitoring and diagnostic centers. We combine that together to give us a digital twin. So what is a twin? A twin is a living, learning model of an asset. We've always used models. We've done it usually when we go to design something, we start with a model and then we use that model to simulate a few things before we design it. But then we usually stop because after you build it, it goes out into the field. In services, we might. If we have a big problem, we may design another model out there or update the model we have to look at the problem in services. And then we put that model away. What this is, though, is that once we create that model, and it's focused usually on a specific thing we're looking at or a specific situation. You don't have to have a full-blown model of every aspect of the asset, but specifically what you want to look at. And we build a living learning model, which means the model gets updated every time data comes in. Whenever our jet engines land, we take a small snapshot of data and we update the model. Every day with our steam turbines or gas turbines, we take the data in from them, we update the model. It's a living model. Then it's a learning model. We look at other parts of the fleet in which they have very similar assets. This asset is the same configuration, operating in a similar environment, being operated the same way, and we learn from them. Maybe they will see a fault or failure before. Maybe they'll see a cyber attack before. We bring that learning into the model we have. So it's a living learning model. What does it do? It drives insights. That's the first thing you see. It will tell you things like when you think something might fail, it'll give you an early warning. It can predict the level of failure, predict the amount of damage you'll have by the time it comes in for repair. So you'll know you could replace parts. You'll know you need this many parts. You will know that, well, I better bring it in earlier because this thing is actually, the parts are being damaged at a rate that I didn't expect because I'm using it differently. And you can also use it to optimize things. So you get the insights. Now, once you get the insights, now you have to translate that into work because that's how money is made. If I have an insight and I do nothing on it, there's no way to monetize that or no way to get things better for a customer. So I actually use workflows, digital and human workflows, to actually do things. Like I can use a workflow to change, in a control center in a grid. I can do things there. Or I can actually go to a control system, the Mark 6C that runs in our GE turbines, and I can actually automate that control system. Or I can actually send a technician out, and the technician could go out and see if there's a problem. Or I can have, on the usual repairs, I can send information to a robot and have that robot take specific pictures of specific areas of the turbine so I can get more insights because I think there are problems there. So now I do the work process, and that work process gives me a result. And I use that as feedback to this twin, and that feedback gives me more insights and can deliver more value for customers. Occasionally, we find things out by using these twins for a long time. Like in aviation, we believed that the greatest stress on the shroud, the area around the turbine, was when the actual aircraft was taking off. We found out by using the twins and understanding the data that really it occurs during climbing, when these aircrafts are at significant heights and then climb even more. Again, that allows us to do design. This is the digital twin. Both giving us the insights and then actually generating a lot of software and automated workflows with some human interaction to deliver value. Now, if you go to the next page, I'll tell you a bit about that value. So this is all in our space, delivering significant value from us using these analytics. Now, here's some examples, especially in the energy space. So there are three things we look at that are of value to the customer. Can I give you early warning about an asset for failing? If I give you early warning and you can take an action, you can do a minor repair, you can change the operating parameters, and that keeps the asset running, that increases the asset's availability. Key for us. So one good example here is what we've done with one of the condensers here, which is collecting enough data from the condensers and understanding, how they were designed itself and how they operated. We can actually predict fouling, right? We can predict the level of fouling in a condenser. We can go and have that cleaned before. And if we have that cleaned at the right time, these things don't fail, or they take a minor amount of time and it increases the availability. The key, though, is to predict that enough time in advance that you can take an action before it impacts your production of energy, right? And these condensers are vital, especially in these combined cycle plants where we actually are taking the heat off of the turbine and using that heat off of the gas turbine and using that to run the steam turbine, right? And so what you see here is the ability to do that and get predictions early enough so that you can keep the availability as high as possible. Second thing we look at is continuous prediction. So what we do here in many cases for these wind turbines, you sign up for something called a PPA, right? Which is a purchase price agreement. It's over multiple years. You agree that I'm going to deliver so much energy over so much time. And what you do then is you have to keep to that commitment. Now, the interesting thing is to keep to that commitment, there's variations. There's variations in the wind, there's variations in, in certain cases, you have certain types of failures. You've put the turbine in a certain place, and in that place, you are 5 miles down the road for a chemical plant, and a lot of these, pollutants get in the air, they gum up the bearings, they cause other factors. There are a number of things that could happen over the lifetime of these turbines. These turbines last 20 years. So what you've got to do is you've got to actually predict failure you've got to predict not only the failures, but you have to predict when the degradation begins to affect the performance such that you can't meet the commitment. And in that case, what you've got to do is you've got to say, well, there will be times that this happens. How do I actually find a way whereby I can optimize the yaw, the pitch of these turbines so I can generate a little more, electricity at this time, given this wind input, because I know, in the next, week, in the next day, in the next 2 hours, I'm going to have that dip so that you keep that average at a certain level. And so we do a lot of work on that, and that delivers significant value. We've seen in many of the wind farms, given the fact, especially those that are larger than 200 turbines, we can generate millions of dollars of savings. Because why we say savings is that if you don't meet that commitment, you pay a penalty, right? And with that penalty that's been happening, we now can add analytics, add AI capabilities in digital twins, save you from paying that penalty. The third thing you look at is this thing called dynamic optimization. Here's an example, of a combined cycle gas plant. What happens is that we know that there are times of the year when the price of electricity ramps very, very high. When it's very cold or when it's very hot, the demand increases and the price jumps. What you'd love to do is you'd love to overfire your turbine or have that turbine, be ready for those times when the price jumps, and then actually run it as hard as you can to make the most profit then. Most people don't do that. The biggest challenge they have is that this turbine has to be maintained in certain intervals. And every time you overfire them or you actually make them run as hard as they can, you have the ability by doing that to actually cause more damage. And so when you assumed the maintenance interval was going to be a year from now, what if that maintenance interval turns out to be 8 months or 9 months from now? That's a bigger problem because it's all planned. Because you plan exactly when one turbine comes off, when one turbine comes on, and this plan structure is tied to the amount of money you're going to produce and the commitments you've made. So you can't afford to break that, structure in which you've made a commitment that this turbine will only be serviced a year from now. Now, what you can do is there are times you can run inefficiently. Run it so it's not as hot internally. What happens then is that you actually save the life of the part. And then at the right time when the prices are high, you overfire it. You run it as hard as you want. So you've saved life and then you burn up that life. But you do it in such a way that you meet your commitments 1 year from now. That is a digital twin inside. It's understanding the remaining life on the part. That understands how that remaining life is based upon how hot the turbine runs and gathers or banks that life for you and allows you to use it at the right time. That's dynamic optimization. And we have found techniques with customers to save them millions of dollars because, again, when that price peaks, you can make a significant amount of money. And that's what they do. They run it inefficiently, and when the prices are normal, and then they save it for that time when it peaks. And now it peaks quite a lot because now that you have renewables in the mix, there are many times in which people believe the renewables would give you something. You have all this solar, and then all of a sudden something like California occurs in which you have a fire, it covers, you get that coverage from smoke. You don't have the delivery that you think you'd have coming from the solar fields. And again, the price of electricity jumps because it's based upon the demand, and you can stay there and make quite a bit of money. So these are 3 good examples, all focus on the fact that can I give you early warning? Can I predict when things will fail or when you need parts? And can I dynamically optimize to give you the most money? And we've been running these for years. We have seen for customers multiple billions of dollars worth of value being delivered. Let's jump to the next slide. What's at the heart of a lot of this? We all see and understand the data and the analytics that's involved, but let me just draw you to 3 things. One is this notion of AI-enabled analytics, because we've had a lot of models before, right? What's different is we're taking data from multiple sources that allow us to do something unique. The other thing, that we've gotten more insights on is this notion of life. What's key for us is we can understand what's happening inside the turbine, but what's the effect on the life of a part? In many cases, you'll find it's hard to believe, but when we do inspections, we rely on people, and there's a ranking. So somebody would go in during a maintenance interval and they will say, well, is this part damaged? Is it not damaged? Because The digital twin predicted it would be damaged. So then you look at the part, and the human would say, well, it's damaged to a level 8. There's a scale of 1 to 10 that the human actually, registers damage on. Now, how that itself, in some cases, doesn't give you the information you need, because one inspector will say that's damage level 8. One inspector will say that's damage level 6. How do you tune your models when this is so subjective? So now what we have is computer vision. Computer vision techniques that allow us to actually look at the part, use an algorithm to detect the failure. Is it spoliation? Is it corrosion? And then literally measure it. So now I know, a year ago, it was spoliation or corrosion damage. It was this large, right? And I feed that back in the model. A year later, it's that much larger. We have exact actual numbers that allow us to get these models a lot better. So a lot of that is the AI-enabled analysis, a real fingerprint of the source of truth by which you tune the twin. Second one is software-defined controls. Whenever I have an insight on something, I have an insight on what's happening with wind or solar energy, and then I want to tune the systems, there's a control system that sits inside. And so what I'd like to do is combine that with the control system and have that control system run as quick as it can to make changes when needed, to the pitch or the yaw of the turbine itself. So we spend a lot of time understanding these software-defined controls, and they're becoming more and more valuable now because, you can use them in renewables, but also whenever the wind or the solar, fails you, it's intermittent, then you have to actually rapidly start your gas turbines. Again, it's a control system that allows you to actually bring that turbine, from a very low level to a much higher level so that it can actually generate the power that's needed. Again, software-defined controls. So we spend a lot of time understanding how those software-defined controls can work with our digital twins so you tie information and work together. The third thing is the autonomous inspection and repair systems. Like we mentioned before, there's a lot of inspection and repair work we get done. Now, part of it is done when you bring it in, but some of it is done when you go to a customer, you go to a site. And what you want to do when you go to the site or when you actually have it being done, by some of the owners of the equipment, is if you automate it and you give them the tools to do it, you collect much better data. The data is uniform. The data allows you to do the fleet analysis I mentioned before. So we spend a lot of time on how do we actually do these things using robots, specially designed robots with special cameras designed to capture that data. How do you put it on the edge? And then how do you use that to create better digital twins? So these are all of the type of technologies that actually help us build the twins. Now, what I'd like to do, because I've spent the time before showing you the plays that we've been running in the industry. And I can show you a play for aviation, a play for renewables, a play for power, all focused on the fact that I give you early warning, I give you continuous prediction, dynamic optimization, all based upon these powerful digital technologies. Let me show you two that we're looking at, that we've been experimenting with for the last 2-3 years, right? Some of it from funding from the Department of Energy, some of it from DARPA funding. And to give you insights about where we think this is going. So if I jump to the next slide, I'll begin by talking about the first one, which actually is called Humble AI. So let me give you a concept of it, and then I'll walk through the slides here. So we do things like digital twin because they deliver business value. Now, after you've shown that business value, and you begin to go to other customers, the hardest thing is to get that adoption everywhere quickly. Why? Because there's a belief, because you're dealing with humans. And every time you deal with humans who have deep expertise, the notion is, well, I've seen that before, I can do that. I mean, this is my job. And so many cases, the notion is, that AI is a black box. I don't know what it's doing. I don't know why it did it. And so I don't think I want to hand control over to multiple million, in a few cases, billions of dollars of assets to an algorithm that I don't fully understand. So we built an approach called Humble AI. And what Humble AI does is this. Essentially, based upon the data that I have, I build an algorithm, right? I build some of the AI techniques we have. Now, the more data I have, the better, this algorithm is. So that data gives me a zone of competency where in that zone, I know what I know and the algorithm works well. Outside of that zone, if I don't have enough samples or enough data, my algorithm isn't as well. So I know my zone of competency. Once I get out of that zone, what I say is go back and use your deterministic algorithms you've always had, and then allow me to learn from that more data you're collecting so I build my zone of competency. So the humble AI says, I know what I know in my zone of competency. Outside, we go back to what happens before, and then I learn and I get better to increase my zone of competency. That works. We've done this with enough clients now where clients feel a lot better. The chief engineers say, okay, within this zone, I only have this risk to my business. I can look at it, I can see if I like it, I can understand it. And if you say it's going to be better than what I have now I can prove it within that one zone. And once you begin to do this and you test it for a while with them, then it gets expanded more and more. And so they believe the AI is working with them. It makes more sense to them. So here's a great example, one we've done with wind. I have a chart up there, and what you see in the chart is wind conditions over 24 hours. Now, wind is really unique as a fuel. It's a free fuel, but with that, low-cost free version, it has certain dynamics. So the wind varies by every hour in the day. The wind varies by height. So when you look at a wind turbine could be as tall as 300 feet. What you see here in the different bands, if you could look at that small diagram we have here, is that the wind speed varies and the height. If you go at the lower levels, the wind speed may be running at 5 meters per second. At 300 feet, it may be running at 9 meters per second. So it varies, with time of day, it varies with height, it varies with distance between two wind turbines that are quarter mile or half a mile apart. It's very different. It varies by season, it varies by weather event. It is very much varying. So what we found in many of our cases, we have zones. Like that blue band is a zone in which we collected a lot of data. For whatever reason, maybe, that's when we collected the data. Maybe the data systems we have in that part of the world, that's where usually the right operating profile is. It operates in that point of view. Between, for instance, I think here, it's between, 5 and 6 and 7 meters per second. So once you have that, you build an algorithm that works well there. So if the wind is at anywhere between 6 and 7 meters per second, the wind speed, I run my algorithm. If you go to the next chart, when the wind gets above that, say the wind is running at 9 or 4 meters per second in terms of the wind speed, I go back to my deterministic algorithm. Right? I say, you know what? I'm humble. I know I'm not good in this interval. Go back to deterministic. And then what I do is I learn. I bring data in and I learn more and more. It may take me multiple events to learn, to get enough data that I can learn. And it may also be that I do model management. I need certain confidence thresholds before I think the learning is there. So I know what my zone is. And outside of my zone, I use, the deterministic sections. And then if you go to the next chart, I expand that knowledge. So in this next chart, what you see here is now I have more information between 5 and 8 meters per second wind speed. And now the twin itself, because I've run the algorithm works within it, I've adapted that model, now I can run it. And so we've been running these trials for about 2 years. We've done them in several places. The last was across 69 wind turbines. Now we've built that into part of a product, and that product is being, sold right now. Again, we've applied that to renewables. We also have applied that to a good friend in power. There's also parts of this that we're bringing onto the grid. I'll give you one last example here before I stop and take questions. If you go to the next chart, and let me take a second and set this up. It's something called digital ghost. So the notion is our infrastructure. We have seen several, over the last 9 years, several cyber attacks coming at infrastructure in the US and around the world, and it's increasing in frequency. So in many cases, since we designed the asset, and we manufacture the asset, we understand the physics of the asset. Inside a gas turbine is a Brayton cycle. That cycle talks about, when you have heat generated by fuel that you ignite, and we know the fuel, we know the materials we use, that actually allows us to understand that explosion should register this temperature on these sensors. So I have 3 sensors. I know the first one is going to be 100. I'm making up a number. The second one is going to be 120 degrees. The third one should be 140. If that middle one, instead of saying 120, says 400 degrees, I can look at that and I can say something's wrong. Either the sensor is damaged or the sensor's been hacked, right? Because I know in that cycle of physics, that shouldn't matter, because it should be 120. I can then, because I own the control system, I can then do a slight perturbation and see what it turns out to be. If in that slight perturbation it's still wrong, now I could begin to understand a few things more if it's a damage sensor or more if it's an actual hacking attempt. So we call this digital ghost. We have a digital twin that's running. So I have a model that tells me what each sensor should say, given the output I'm seeing, given the different temperatures, given the different pressures. And that model has to jive with what the actual sensors are saying. Because I know the physics. I created the model based upon the physics and the AI. If it does not, I know something has happened. And then I have other techniques I can use to determine if it's a failed sensor or if it's a hacking itself, right? So that is first detecting a problem. Then I can isolate it by saying it's this specific sensor. And then at the right time, I can say, I know that sensor's been hacked. Rather than use that sensor, I'm going to use a sensor that's on the digital twin. So that value that's on the digital twin should be accurate. It might be less so. So there may be slight degradation in performance, but that allows me to continually run my asset in slightly degraded mode and isolate the attack. So if we go to the next chart and we hit the play button, I want you to watch this video now that you have that background. And so the notion here is that's a digital twin that we've created. Whenever there's an action where something overheats, we're looking at the digital twin and we're saying, is that action being caused by a sensor, a problem, or is it because somebody's trying to hack the system? And so I can use that twin to go in and determine if there has been a hack. And if there has been a hack, what I do is I just take the digital twin and I use that model as the input to my control system instead. And again, I can continue running my turbine to make sure I can still produce electricity while isolating the problems that I have. And this is deeply invaluable, to many systems out there, whether it be something that you see as a result of a problem that's occurring because of a failure in the sensors or failure of some control pieces or deliberate hacking. Now, we've been working with the Department of Energy on this for several years. In fact, we then took it to our Greenville test site. We have a huge gas turbine that we run there. We tested it there, and as a result of it, it does work. So we had a number of the government officials come in, together with some of our friends in the military, test it against certain capabilities. We see it works. So these are the kind of new capabilities that we're building, that we're bringing to bear. So let me go to our last chart here. So let me summarize with just a few key points. So I think there's some things, that I would put to this August body to consider. As we watch this unfold, you have to really be aware of all these forces, because while there's an altruistic bent, at some point we've got to deal with the financial aspects of it and tie both of those together. That allows this to happen. So these market forces are very powerful. These digital forces that are happening, that are constantly lowering the amount that you pay and improving the performance, the things in the consumer space, can we bring these across? Can we bring these to our space and use those as great sources of information and capability to actually figure out insights as well as drive workflows? And then the last thing is, can you understand what other technologies we should focus on? I love the discussion we had before about blockchain. Blockchain is great. Blockchain allows me to get traceability, so I can understand which parts are actually in what configurations. Because again, I need to know the exact parts in each asset so that I can actually use the right digital twin. Because if I have a digital twin assuming this is a 9F03 configuration versus a 9F04 configuration, The parts are different in the O4 configuration. The parts have different tolerances. I'm using the wrong model. So I need that traceability in things like blockchain to ensure I actually know what configuration, what's in the asset when I run the models. So there are many new technologies, new techniques coming in. 5G is another great one. Can I get more data? More data? Can I get lower latency? I can do more things with more data in terms of better insights. With low latency, I can activate my control system even faster. So I put these things together, and then what I need to do then is understand the business transformation process. You know, how do I show value? How do I increase adoption? How do I remove the cyber risk? Because the other thing you deal with is every time you talk to customers and they say, well, if I put in all this digital technology, wouldn't that make me an even bigger target, you know, for cyber attacks? And again, risk the reputation, you know, risk, first of all, you know, my delivery to customers, and risk my reputation. But in the end, we all know that this is what the industry is going to be. Digital aspects of this industry are going to profoundly transform it with the next energy transformation. So I think you're in a beautiful place, and it's my delight to spend the time with you and show you what little we have done so far. With that, I will turn it back to Dr. Murray and open it for questions. I think we have a few more minutes of questions. I hope so, at least.
Thank you so much, Colin. That was such a fascinating presentation. I'm afraid of all the questions I wrote down, it would take us another 45 minutes just to kind of go through them. And so I'm going to defer to the audience here, who put a number of great questions here in the Q&A. And so one I'm just going to start with sort of a general, it's almost like career advice. We have a lot of early career data scientists in the audience right now. And so, you know, question to you. You know, you're a few years into your career. You've seen a lot happen after 2 decades at IBM and I think roughly a decade at GE. So what advice would you give to soon-to-be graduates or someone early in their career as they're preparing to start a career applying data science to real-world energy applications?
I'll give 2 pieces of advice. So one, you know, and all of the advice comes because of my failures. You know, I have failed royally. That allows me to actually give good advice. First thing is you're skilled in what you're skilled in terms of data science. Spend time learning about the processes. Spend time learning about the environment in which you're going to apply that in, right? So when we talk about the energy transition, there's several things going on. So for instance, one is climate. Okay, we want to create new renewable capabilities. But the second thing is defense. So for instance, right now we know that there are multiple different actors out there, and these actors are all saying we want to wage total war. They'll attack your infrastructure systems, your financial systems. So there's a significant amount of money being spent by the US government to protect these systems. Can you understand the way the US government thinks? Can you understand their economics? Can you understand what motivates them? Spend some time getting that. Then if you understand what's happening in the business world, you understand what's happening in the government world or the policy world, it sharpens your delivery of your technology. Because the game always is taking a business or a government problem and convert it into a data problem to a data solution, and then you got to get that data solution back to a real world solution. So you have to understand the context by which you're solving the problem to be most effective. So spend the time on that. That's the first thing I would say. Second thing I would say is, for me, 2 things become important. Well, 3 things. The first thing is awareness. The more awareness you get about what's going on around you, the better off you are. So attend these conferences, spend time at Duke with the Energy Initiative, make friends, because that gives you a greater awareness. After that, think about resiliency. You are going to fail along the way in what you try to do. Take that blow and get back up. And the third thing is learning, right? I mean, you have to learn continuously. I made the mistake of believing when I finished my PhD at Berkeley that, well, you know, that's good enough. I mean, I think I've done it. I've written the stuff I've written. That was wrong. Every 2 years, I had to continuously learn. And now I realize the learning, the rate of growth is happening so fast. Like I look at my PhD at Berkeley and you look at my bibliography and you see things that are 2, 3 years, 5 years old, and you say, that was okay. Now, when you look at some of the PhDs out, you know, stuff in the bibliography is at most 2 years old. So you could only learn so much. So you've got to not only learn yourself, but you got to have friends who are learning other things and reach out to them. So your learning is not you, your learning is your network. So think about awareness, get the world in a broad context so that you could see many things that will help you understand where to go. Think about resiliency. You're going to feel along the way it doesn't say anything about you. It's the nature of the world. And think about learning. You will have to learn, and you will have to get into networks in which your friends are learning, and use them as well, because you can't learn it all. So that's the advice I'd give, Brian.
That's great too. Ask the right questions, be a lifetime learner, and be resilient. And I think, you know, I don't know if there's going to be a keyword for 2020, but resilience, I think, is going to be at the top of the list for me. So a couple of other questions. With AI-enabled analytics, you talked about computer vision to make inspections more objective. Given this idea, does this sort of system have to be rigid? And I guess by that, I mean, you know, it's like we were talking about, like humble AI or something like that, where there's a little bit more interaction with the humans. I don't know if that's what the question
is. Yeah, let me address that part of it too. That is quite right. You know, a lot of the work we do in computer vision, we took, the great thing about GE is GE as a GE healthcare system. So we took a lot of what we learned from how radiologists view things. So what radiologists do is, what we do is our systems indicate the areas the radiologist should look at. I'm not making the decision for the radiologist. I indicate the areas. The radiologist then looks at that decision, looks at those areas, and then they focus on those areas. If they find something else that I didn't cover, they make a circle themselves. And so the AI system learns, I didn't know that, and we capture that information as well. So we do the same thing right now in analysis for aircraft systems. We initially have the AI system figure out where are the biggest problems, and it puts circles around those. Right? And the human will tick off the circles, and then the human will draw a blue box around things it missed. And so the AI system gets to learn along the way. Then by and by, we call that assisted. And then augmented is when we get to a point in which the human says, you know, it's discovering most of these things. Don't show me all. Just show me the areas where you're unsure. So now what the system does, it says, I know enough about capturing the basic things. I'm just going to show you only the high-level things, the things I'm not sure about. So now you actually only use the inspector where the system is not sure. So it always is going to be a combination of human and AI for one simple thing. I need to detect a problem as early as possible. I may not have enough data to actually train an AI system. So if the failure is now occurring, I need the humans to figure that one out first. And so we always bring them together. There's no system that we have in which it's just the AI by itself and the human without human supervision. It works together, given the dynamic nature change we see.
Yeah, I mean, one of the questions I had coming in was just thinking about what are some of the lessons that you've learned from applications in other sectors to energy. And as I heard you talk about, you know, digital twins and digital ghosts and humble AI, it's like they've got to have come from health. They've got to have come from aviation and manufacturing.
Exactly.
Because you literally, you're trying to avoid building the plane while you're flying.
Exactly.
And those are the types of problems that actually apply in energy and across other sectors as well.
Perfect. Exactly.
We have a question up here that is self-serving for a lot of people in the audience, which is a question about does GE have data science research partnerships with universities? And what kind of research do you do in partnership with a university versus in-house?
Yeah.
If you have.
Yeah, we do. We do. I mean, and again, we have many. I deal with a few. I spend time with the University of Maryland, Baltimore County. I spend time as well with some of the work that we've done in Stanford. They usually fall into two categories. GE has something called the Global Research Center, GRC. And this is where we spend a lot of time working with universities on cutting edge pieces. And we also have our GE businesses do work with the universities. The best way I find to do that, usually what we do is we get together, we spend time, we share our views, and then we try to combine our ideas and go after a DARPA, Department of Energy, IARPA-E proposal. And that pulls us together. Because what it does, it allows us to find ways to work together in a construct that makes sense. And usually when you do these right, the IP gets taken care of. You understand how it works. It's a multiple year contract. And that allows us to actually build the research moving forward. Then as that progresses, I have the ability to go from the work I'm doing in the Global Research Center and tie it into one of the GE businesses. Because the real power is when you can take that research and put it in a product, get the product out there. And we can turn around and sell that product right into the U.S. military in terms of jet engines. We sell, gas turbines across the world. So we have a way of teaming, working together on, especially with government projects, and then from there going to products. And I think that flow makes a ton of sense. Now, not everything gets into a product because, again, not everything is at the right time. But we do this piece of research, and I think the best way is to do things tied to some of the government initiatives we have, especially in energy.
Okay. So this is going to be the last question. If I could ask, even though it's a big question, I just ask you if we could just maybe have like a 1-minute answer, and then we're already a little bit over, and I think we have to move on. But it has to relate to the kind of the crisis of our time. So how is the AI system and tech adapting to shocks that don't have a historical reference or data to learn from, like the COVID crisis?
Ah, boy. Yeah, that's a big question. In a one-line sentence, what would I tell you? I don't know how to understand it in a one-line sentence. We have seen that affect our supply chains because all history changed when this occurred. What we have found, though, is that there are AI, for instance, the recovery in COVID in our airplane business. We had models that are no longer valid. We've been looking at things that are happening in China. China is recovering first from the pandemic, and then we can use AI techniques there to show us how to actually augment the current models in order to get them better. So there are AI techniques that can be used, right, with sparse data. We have deliberately built some like that with sparse data that could be used. And then what we do is we have feedback loops, because again, I don't depend upon a model with sparse data, but I have a rapid feedback loop to tell me what was wrong, what was right, and I update it. So there's certain types of learning that we use to do that. But we have ways of doing it, yes.
That's great, and thank you. That was a terrific 1-minute answer to a 2-day question.
Yes. Well, it was my delight to be here, Brian. It's my delight and honor. Thank you for having me, and hopefully that added to your seminar.
Oh, very much so, and the honor was ours. So thank you so much. In whatever way you can do, and wherever you are, please join me in an applause for Dr. Colin Parris for a really stimulating keynote.
My pleasure.
Thank you.
Thank you. Have a great conference.